Okay, I will start now. Okay.
Yes.
Okay. So, hello and welcome all the TY-BSc students from Konkan region for live online lecture series for TY-BSc physics student of the Konkan region by Professor D.B. Rane, Department of Physics, Barrister Balasaheb Khardekar College, Vengurla. This is particular the lecture for electrodynamics, semester 5, paper number 4, right? So,
Hello, sir.
hello.
Okay.
Hello. So, is online lecture. Online lecture on
lecture la.
okay. So all the students of TY-BSc Physics of Konkan region, you are welcome for this online lecture series. Online lecture series by Professor D.B. Rane, Department of Physics, Barrister Balasaheb Khardekar College, Vengurla. Through this lecture, we are going to discuss the semester 5 paper number 4, that is electrodynamics, and very first unit of the electrodynamics, that is what we are having, the electrostats. Have introduction, right? So today we will consider the first topic of the unit number 1 for TY-BSc Physics semester 5, which includes Gauss law and its application. But before that, we should consider the very basic law of electrostatics. That is what the Coulomb's law. And before that, we should know what is electrostatic. Electrostatic, what is it actually? You should have some clear idea about the electrostatic. So I have written here in my PPT, actually in plus side, you can have what is electrostatic. So it is what? The study of effect produced by static electric field, that means non-time varying electric field, or the electric field produced by the static charge. Actually, electrodynamics is a very vast topic. Actually, it start with the static electric field produced by the static charge. Of course, it is not time varying, and during the course we will consider the time varying electric magnetic field, time varying electromagnetic field, and finally we will reach the uh, description of electromagnetic disturbance. Of course, it is coming from sun to earth, that is the light, sunlight. So that description is there. Finally, we'll have that. So let us start with the first topic, of course, the electrostatic, and here we'll having the electric field produced by the stationary charge, that is plus q, in the vicinity of that particular charge. Now here in this case, I have shown the diagram. I have shown the electric field here produced by the positive charge plus q, and of course these lines, these arrows are the direction of electric field, right? So here also we are having the negative charge, because we are having two types of charges here, positive charge and negative charge. The lines of force or electric field lines, they are coming to the negative charge. So this is the convention actually, the electric force and electric field intensity. So that is what. Now here we are having the electric field produced by this. Now all these things, whatever effect produced by this particular positive charge or negative charge, it is governed by the very basic law of electrostatic, that is Coulomb's law. That is Coulomb's law. So first of all, we should consider that Coulomb's law, right? So next. So here we are having the statement of Coulomb's law. Very basic law. We have learned all these things from 11th standard, 11th science standard also, right? So this is what. So we'll have very clear idea about that in this particular lecture first. So this is the statement of the Coulomb's law. So what is that? The force of attraction or repulsion between given two charges is directly proportional to the product of the magnitude and inversely proportional to the square of the distance between them. I have shown here the representation or the position vector of q1, position vector of q2, that is r1 and r2, with respect to this Cartesian coordinate system x, y, z, and we are having the position vector of q1 is r1 and position vector of q2 is r2, and the distance between between q1 and q2 is r21 vector, right? Now here the charge q1 and charge q2, they are of same nature, that is positive charges are there, therefore there is force of repulsion. So Q2 will exert the force in Q1 charge, and Q1 the force on Q2 in this direction, that is, they are equal and opposite, right? Equal and opposite is minus F. Now convert this particular statement in mathematical form. So what is that? The force of attraction or repulsion is proportional to q1 q2 divided by r21 square with the direction of vector r21, right? So this is the statement, mathematical statement. This proportionality should have proportionality. So here also we are having F is equal to 1 upon 4 pi epsilon 0 q1 q2 divided by r1 r21 square. But here we got the formula for force of attraction and repulsion. But we should think, or we should say something about why it is so. So the idea of this particular formula of force of attraction or repulsion is, I think it is taken from the very basic law of classical mechanics, that is law of gravitation. What is there in the law of gravitation? The force of attraction between two bodies, that made by, of course, the Newtonian, made in the Newtonian physics, that is classical physics, and two masses exert the force of attraction between on each other by F is equal to g mm. Universe. Now, here also we are having same formula. And here it is the constant of proportionality G. So they are similar formulas. We should consider what type of material is present between Q1 and Q2. That material decides how much force will be exerted, or force of attraction or repulsion between Q1 and Q2. So that should be the property of that particular material. And finally, what property? So that is the electrical permittivity of the medium between Q1 and Q2. And that is, here in this case, the free space is there between Q1 and Q2. Therefore, we have used epsilon 0 there. Therefore, finally, we have the force acting on charge particle Q1 and Q2. In case of this Q1 and Q2 positive, it is force of repulsion, of course. And therefore, this is the formula for that. Now we'll go for the next. Now these are the effects of force of repulsion, and how we can connect these three quantities, because force of attraction or repulsion will create the electrostatic field around that particular charged particle, right? Then you can have the electrostatic potential also, then you can have the electrostatic energy also of the assembly. So one by one we'll consider all these things, right? So first of all, this is intensity of electric field, intensity E, right? The intensity of electric field is nothing but the force per unit charge in that particular field. Here I have shown the electric field or electrostatic field, more correctly electrostatic field created by or produced by the plus charge q in the vicinity of that particular charge. Then what should be the intensity of that electric field? So by definition, it is force per unit charge. So here we have force is equal to 1 upon 4 pi epsilon जो capital Q divided by R square multiplied by 1 coulomb there. So 1 coulomb is nothing but this is unit charge, right? So this formula becomes for intensity of electric field becomes 1 upon 4 pi epsilon 0 Q divided by R square, and the direction is specified by the direction of the radius vector. So these arrows are the direction of electric field, and of course you will have some idea about the electric flux also. These are the lines or lines of force, you can say. So this is the electric flux produced by plus charge capital Q, right? So this is actually the formula for the intensity of electric field at distance small r from positive charge plus Q. Okay, now we'll go for the electrostatic potential of electric field. So by definition, what is electrostatic potential of the produced by the charge? So it is what the electrostatic potential is nothing but the work done in bringing unit positive charge from the infinity to that particular position at r, right? So what it should be? It should be the work done. It should be the work done. And how it is? Work done is nothing but what? Force into displacement. So force into displacement on unit charge, we have the force equal to 1 upon 4 pi epsilon, that is 1 upon 4 pi epsilon 0 Q divided by I square is the force on unit charge, right? So this is E is the force on the unit charge. So that is we have taken here multiplied by the displacement. How much displacement we have made? Actually from plus q to distance r. So we have to multiply by that r with this e. So we'll have r square will get cancelled with that r, and only r will be there in the denominator. So what is the electrostatic potential produced by plus charge q in the vicinity of the charge is given by Vr is equal to 1 upon 4 pi epsilon 0 q divided by r. So this is what we are having. Now here we are having a special relation between E and V. Why it is we need this particular? Because when we are going for the calculation of electric field intensity, electric potential, in practice, when we are having the charge distribution there, in some problems it is very easy to calculate E, and in some problems where it is very easy to calculate V. So if we have value of E, then we can convert that particular in terms of V also. So to convert E from V and V from E, right, we need some relation between E and V. So this is the relation, very famous relation between E and V. Here electric field vector, electric field intensity E, and it is of course the minus gradient of V. Now this is V is a scalar quantity. Therefore, if you take the gradient of V, then it will be E. So let us take gradient of V is equal to, here we are having one dimensional, that is one dimensional gradient. So it is minus d by dr of that V. So it is 1 upon 4 pi epsilon 0 Q divided by R. And if
सर तुमचा आवाज येत नाहीये.
Review of Coulomb's law. It's okay, sir.
Yes, sir.
Okay. This is about the review of Coulomb's law. Now, one another quantity remain there in the discussion, that is the electrostatic potential energy, that is capital U21. I have given here the formula for that, Q1 Q2 divided by 4 pi epsilon 0 R21. Actually, what is it? Actually, the electrostatic potential energy is nothing but the total work done in assembling that particular energy, that particular system. Therefore, here we are having the system of two charged particles. This is Q1 and Q2, right? So first of all, when we keep Q1 charge at some position, there will not be any work, because there is initially there is no electric field or electric field there. Therefore, there is no need to work against that particular electric field. Therefore, when we are keeping this second charge at the position from the at distance R21 from first charge Q1, then we need to work against that particular force of repulsion, because here we are having both the charges are positive charges. So force of repulsion will be there, and we are bringing that particular Q2 charge from infinity to that position R21, right? So we should we should have the work done against that particular force, and what it will be of course the force into displacement. And here we are having the definition of V as work done in bringing unit positive charge. So here we are bringing Q2 amount of charge. So how much work will done in that particular process, in that assembly, in the assembling of that particular system will be simply you have to multiply by Q2 to Q1 divided by this is the amount of work done in assembling this particular the system of two charged particles having charge Q1 and having charge Q2, and the distance between two charges is R21. R21. Okay, so this is about the effect of electric field. Okay, effect of electric field. Okay, so now we'll consider the actually the syllabus for TY B.Sc Physics, paper number 4, that is Gauss Law of Electrostatics and its applications. So here I am having here the statement of Gauss Law, that is total outward electric flux phi e through a closed surface in free space, it is equal to 1 upon epsilon 0 times the total electric charge enclosed by that closed surface, right? So this is the statement of Gauss law. This is the statement of Gauss law. To understand about the Gauss law, the statement of Gauss law, first of all, we must know what is electric flux. What is electric flux? So I have shown here the diagram of electric flux. I am having here a surface area S. Below that surface area, I am having some positive charge, and due to that positive charge, there is production of electric flux, and that flux is passing through this particular surface area. Okay, so I have shown here by with the lines of force, I have shown the electric flux passing through the surface S, right? Now here you must have what would be the direction of electric field and direction of the surface S, right? So here I have chosen the small surface area dA and with the direction n cap, right? So this is n cap, unit vector n is the direction of dA, right? And at that particular position, the direction of electric field is E, and of course I have shown here the angle between the vector dA and vector E is theta. So theta is the angle between the surface area dA and the electric field intensity vector E, right? So this is angle theta. Now what is that? What is that E? E is nothing but the electric flux through unit area, that is what the electric field intensity E. Now here we are having electric flux is nothing but the number of lines of force passing through normally through that particular surface area, right? And the intensity of electric field is nothing but the flux through unit area, right? So here I can have the flux through is DIE, it is given by E dot dA, E dot dA. What is that? E is what the electric flux through area. So how much will be the electric flux through area dA? Will be E multiplied by dA, is the electric flux through area dA. Now the total electric flux through surface area S will be, we have to integrate this because here we are having continuous distribution of flux. More correctly, this is first density E, so we have to integrate that. In case of discrete distribution, we are taking the summation, and when we are having a continuous distribution of any physical quantity, we are taking the integration of that. So therefore, here I have written the total flux through surface area S is given by surface integration E dot dA, surface integration of E dot dA, right? And now we can represent the Gauss law of electrostatic mathematical form, and I have shown the mathematical form of Gauss law. So what is that? Here it is closed enclosed divided by epsilon 0. So this is the mathematical statement of integral form of Gauss law. Okay. Okay. So this is integral form of Gauss law. Okay. So let us have a proof of that particular Gauss law. So I have shown the surface, closed surface S here, and it encloses the plus Q charge, right, kept at point Q, kept at point P actually. So okay, so here it is a this is what the proof of Gauss law. So this is surface area S of surface, and माझं ठेव ना नेट चालवलं कोणाचं लावलं okay. So this is the proof of we are having here. So here we are having the surface area of this closed surface, right, S, and we have chosen the small area dA here, and the total flux through dA will be given by d of So I have chosen here the area dA there. Therefore, the flux through dA will be equal to E dot dA, because E is the flux through unit area multiplied by dA. Therefore, it is, if you substitute there, Q divided by 4 pi epsilon 0 R square dot dA. So dot product of this E and dA, so it will be cos of theta. So it is Q divided by 4 pi epsilon 0 R square cos theta into dA. So this is what. Now, what is this dA cos theta divided by R square? By definition of solid angle, this is d omega. D omega is what the solid angle subtended by area dA at position P, that is the position of Q, right? So that is d omega there, right? So d phi E is equal to nothing but Q divided by 4 pi epsilon 0 d omega, d omega. Okay, so total outward flux phi E we can calculate by taking the integration over the complete closed surface, complete closed surface, and there of course you are having closed surface integral d phi E is equal to closed surface integral over S. So you have substituted for d phi E Q divided by 4 pi epsilon 0 into d omega, and as Q is constant, 4 pi epsilon 0 is constant, you can take outside the integration and take the closed surface integral of d omega. So what is the closed surface integral of d omega? So it is of course the solid angle for any closed surface. Solid angle for any closed surface is always equal to 4 pi. So integration of this part will be equal to 4 pi. Right. So if we substitute this 4 pi for this total integration, then phi E is equal to Q divided by epsilon 0. Epsilon 0. Okay. So this is what we are having here. Phi E is equal to. Now we can use this phi E for the Gauss law. Therefore, of course, we'll have the integral form of Gauss law as closed surface integral S E dot dA is equal to Q enclosed divided by epsilon 0 by that particular closed surface. Okay, so next we'll go for the next thing, that is we should have the conversion from integral form to differential form of Gauss law. So here we are having the integral form of Gauss law, and how we can go for the differential form. So this is what we are having here. So closed surface integral E dot d is equal to Q divided by epsilon 0. But here we can represent Q in terms of volume charge density of that particular object, right? So this is Q is equal to volume integration rho dV, because rho is the volume charge density of the object, right? So Q, total Q of that particular object is equal to volume integration rho dV. Now we can substitute for that. So it is closed surface integral E dot dA is equal to rho divided by epsilon dV. Now here we are having at one side we are having volume integration, and another side we are having a closed surface integral. Okay, so to equate these two, we should transfer this surface integral into volume integral. How it can be? So use the divergence theorem. So you can use divergence theorem. So closed surface integral E dot dA is equal to volume integration divergence of E dV. But this is applicable only when this particular surface, closed surface area S, encloses the volume V only. So this is the condition over this transfer. So here we can transfer this. This is volume integration divergence of E dV is equal to volume integration rho divided by epsilon 0. Now these are both the sides are volume integration. Therefore, this quantity over which we are taking the integration, that must be same. That means if the integration of two quantities is same, definitely we can say the quantities are same. Quantities are same. So here I am having del dot E is equal to rho divided by epsilon. It is del dot E is equal to rho divided by epsilon is the differential form of Gauss law. Now here one another thing has to be clear to you, that is what we have considered in Gauss law is if there is charge inside the surface, then only the outward. Now, now, now here check here. What happens if there is any charge outside the closed surface? Outside the closed surface, we can consider any charge Q which is outside this closed surface area S. This is the charge Q outside this. Now, simply speaking, I can have some derivation for that. To prove that E is equal to 0, right, inside this closed surface S due to this charge plus charge Q outside that closed surface. But simply speaking, here I can show this. The total outward flux will be equal to 0, because here the flux produced by this charge Q will enter the area dA, and the direction of area dA is in this direction N1, and here the same flux is going out from area dA2, and the direction of this dA2 is N2, and same solid angle is subtended by area dA2 and area dA1 at point charge Q. Therefore, this solid angle subtended by this dA2 and dA1, they are equal and opposite. That is minus d omega 1 and equal to the solid angle d omega 1, right? So they are equal and opposite. Therefore, the net outward flux becomes 0, right? Because this charge is outside the closed surface. So that can be explained using this. So when we are having electric field inside or outside the closed surface, only the contribution from enclosed charge will be there. No contribution from the charge which is outside the closed surface. So that has to be very clear to you, because when we are going to consider the actual applications of Gauss law, there we are using this particular fact, right? So let us go for the application of Gauss law. The first here I am having here, I will read this particular problem. So compute the electrostatic field in free space due to a charge conducting sphere of radius capital R carrying a total charge Q, capital Q, at any point outside the sphere or at any point inside the sphere. So here we are having a problem, right? So what problem is there? So here we are having a solid sphere. Of course, it is of conducting material, and the radius of sphere is capital R, and the total charge on this sphere is capital Q. Now, as this is a conducting sphere, the total charge of the sphere will reside on the surface of the sphere. No charge will remain inside the sphere. Is it clear? Why? When there is conducting media, no charge will remain inside the conductor. It will remain as they reside at the surface of the sphere. Here we are having a sphere, and the whole charge will reside on the surface of the sphere. This is very important to know or understand, right? So one by one we'll consider for this. For now, we have taken the point charge, point P at the outside the conducting sphere at distance small r from the center of the charged sphere. So this is the first point that has to be find out. So here the r is greater than capital R, therefore phi is equal to, of course, using Gauss law, statement of Gauss law, closed surface integral E dot dA is equal to closed surface integral. Of course, you find out the dot product of these two vectors. So it is E dA cos of theta. Theta is the angle between E and dA, of course, at that position. Therefore, cos theta. Here always we are having the for any dA we are having the angle between E and dA will be equal to 0. will be equal to 0. So cos 0 or cos theta is cos 0 is equal to 1. Therefore, closed surface integral E dA will be there, cos 0 is 1. So here we are having electric field which is constant, right? So you can take outside the integration and closed surface integral D. So what is closed surface integral D? Of course, the surface area of this Gaussian surface. This is dotted line is a Gaussian surface, right? So it is, of course, it is 4 pi r square. So value of this integration, closed surface integral, is 4 pi r square. So if you substitute that, then you will find that pi e is equal to E multiplied by 4 pi r square is equal to, according to Gauss law, it is Q enclosed divided by epsilon 0. This is Q is the total charge on the sphere. So it is E is equal to 1 upon 4 pi epsilon 0 Q divided by r square for r outside the sphere. So this is the formula. You can calculate anywhere outside the sphere using this formula, the electric field intensity. Okay. Now the next thing is what? If r is smaller than capital R, that means the point P is inside the sphere, charged sphere, inside the sphere. Okay. Now, when we are taking this Gaussian surface at distance r dash from the center of the conducting sphere, then we will find that as this whole charge is reside on the surface of the conducting sphere, no charge remain inside the sphere. So inside the sphere, Q enclosed is equal to 0. Q enclosed is equal to 0, right? Therefore, E will be equal to 0 inside the sphere. So inside the sphere, what happens? The electric field intensity is equal to 0. But what about the electric field? Electric potential, it will not be 0. It will be constant, because derivative of electric field intensity, electric potential is equal to E, Here E is equal to 0, but V is not equal to 0. V is equal to constant inside the sphere. So this is about the electric field intensity outside the sphere, inside the sphere. We can calculate the electric potential outside the sphere and inside the sphere using the formula E is equal to minus gradient of V. Now here we are having another example, but here is the case of non-conducting material. Here is the same sphere is there, but it is non-conducting. Now the total charge spread over here, this sphere is spread all over this volume. Now here we are having the total charge equal to 4/3 pi r cube multiplied by rho. What is this rho? Rho is the constant volume charge density over this non-conducting sphere. The charges inside the sphere will remain as it is inside the sphere, right? So this is the problem of non-conducting material. So when we are calculating for a point outside the sphere, r will be greater than that, and you can find out pi e is equal to closed surface integral. This is according to Gauss law, and everything will be same as in the conducting medium. Then you can have E is equal to 1 upon 4 pi epsilon 0 Q divided by r square. That means outside the sphere there is no effect. It will enclose the charge. But when going inside the sphere, that is r is smaller than capital R, then it will become different from the previous case. So phi is equal to surface charge, closed surface into E dot dA, and you can have the same thing here. So it is E is equal to 4 pi epsilon 0, 4 pi r square, and you will have phi E is equal to Q divided Okay, so this is second case. Actually, here we have change in this enclosed Q. Now, what is Q enclosed in that particular Gaussian surface? It will be Q is equal to 4/3 pi r square multiplied by rho, but it is spread over the complete sphere. Therefore, we should take Q enclosed is equal to Q R cube divided by capital R cube. Therefore, E is equal to 4 pi r square Q R cube divided by R cube epsilon 0. Therefore, here in this case, what we'll have is E is equal to 1 upon 4 pi epsilon 0 Q R divided by R cube. Q. Now, this is change in the expression for electric field inside the charged sphere, right? Now, if we represent this particular graphically, this is what the graphical representation of electric field intensity from the center of the non-conducting sphere up to the radius capital R of the sphere and outside the sphere. This is outside the sphere. This is outside the sphere. So here, in this case, from the center of the sphere, the electric field intensity is proportional to R, right? At the surface of the sphere, it will become the electric field intensity. Electric field intensity become Q is equal to E is equal to Q divided by 4 pi epsilon 0 R square. And outside the sphere, it will follow this inverse square law. Inverse square law. So it is outside the sphere, it will follow the inverse square law. Inside the sphere, it is proportional to R, and at the surface of the charged non-conducting sphere, it will be the electric field intensity will be Q divided by 4 pi epsilon 0 R square. Okay, let us go for the next. Let us go for the next problem. Here we are having infinite plane, charged infinite plane, right? So to consider or to find out the electric field above this above this charged plane and below this charged plane, I have shown the direction of electric field above this conducting plane and below this conducting plane. So to apply this particular Gauss law of electrostatics, this particular case, we should have a very small pillbox, right, with the surface area S1, S2, and curved surface area S3. All of this S1 is having area A, S2 is having area surface area A. Now we are going to find out, this is pillbox, so we can apply this for the apply this Gauss law for this pillbox. So of course, the total outward flux through the going out from this pillbox is given by phi is equal to closed area E dot NDA. What is this NDA? NDA is the unit vector along the direction of vector dA, right? So we separate out this complete closed surface area into three different surface area. So total surface area of this pillbox is say S, then it will contain S1 plus S2 plus S3. Okay, so this is what we have separated this closed surface into three surface areas S1, S2, and S3, and we have applied the Gauss law. As okay, so E dot here in case of third surface area, that is S3, what we have is E dot N3dA is equal to E dA cos of theta between N3 and N3 and E. So what is the angle between N3 and E? It is 90 degree. Therefore, cos of 90 is 0. Therefore, the contribution of this third integration goes to 0. phi E is equal to, let us go for this, S1 surface integral S1 dot N1 dA plus S2 dot N2 dA. So contribution from surface area S1 and contribution from surface area S2. So it is of course EA cos of 0 degree, EA cos of 0 degree, cos 0 is 1, therefore phi E is equal to 2E into A. A is the area of this S1, same area S2 is having their A. So it is phi E is equal to EA. Therefore, the charge enclosed in this pillbox is sigma into A. This is because sigma is the surface charge density and A is the area of the pillbox, cross-sectional area of the pillbox. Therefore, phi E is equal to Q enclosed divided by epsilon 0 and phi E is equal to sigma A divided by epsilon 0 is equal to twice EA. Therefore, above the this plane, you are having electric field intensity sigma divided by twice epsilon 0, and the direction will be given by the perpendicular direction of this particular charged plane. And below also you are having the same intensity of electric field. Now we'll go for the next problem. Here we are having, in this problem we are having two parallel conducting planes with surface charge density plus sigma and another plane with surface charge density minus sigma. So here we are having parallel planes and with same charge density but in opposite in nature, right? Plus charge density here and negative charge density here. So what will be the electric field intensity, position of electric or value of electric field intensity in all the three regions? This is region number 1, region number 2 and region number 3. So we can find out what is the electric field here, what is the electric field here, what is the electric field here. Now we consider the region number 1. So E plus what? What is this E plus? E plus is the electric field due to positive plate. So it is sigma divided by twice epsilon 0 as we have considered in previous case. And E minus is the electric field produced by the negative plate. So it is sigma divided by twice epsilon 0, right? So here I have shown the different directions or electric field in three regions. For due to positive plate, you are having, this is the electric field intensity in this first region. This is E plus in second region, E plus in third region. Now this is what the electric field intensity due to negative plate, and this is in first region, second region and third region. Okay, is it clear to you? This is direction of, because right. So this is so in first region electric field intensity due to positive and negative, they are same in magnitude and opposite in direction. Therefore E first is equal to 0, right? They cancel out each other. Now in region number 2, what happens there? Electric field intensity E plus and E minus, they are in same direction. Therefore they add together to form E second is equal to sigma divided by epsilon 0, sigma divided by epsilon 0. And in third region, same thing is happening there. E plus and E minus having same magnitude but opposite direction. Therefore, in third region also you are having E third is equal to 0. So this is the best example. Okay, so this is about the how we can have the electric field between two parallel plates, charged parallel plates. Charged parallel plate. Okay, so here we are having another example of this. So what is this? A closed conductor carrying surcharge density sigma compute the electrostatic field in free space at a point just outside, but it is very close to the surface. So here we should consider this particular charged sphere high density plus sigma, and here we have considered the Gaussian surface, but this Gaussian surface is very close to the surface of the conducting sphere on which you are having the plus charge density sigma, right? Closed surface integral. This is Gauss law. Phi E is equal to closed surface integral E dot dA is equal to Q enclosed divided by epsilon 0. As Q enclosed is nothing but the surface area of this sphere is say A, then sigma multiplied by A is the Q enclosed, that is enclosed the charge by Gaussian surface. Therefore, E multiplied by this closed surface integral dA is equal to, of course, it will be Q enclosed divided by epsilon 0, epsilon, sorry, sigma A divided by epsilon 0, right? So E dot dA is equal to sigma A divided by epsilon 0. Therefore, E outside the conducting sphere with charge density sigma will be given by sigma divided by epsilon 0. So this is about the, and the out, inside the conducting sphere, the electric field, of course, it is equal to 0, but potential, electric potential will remain constant there inside the charged sphere. Okay, so this is about the Gauss law of electrostatic and its application, simple application. In the lectures, we'll consider next of this lecture particularly. We'll take another examples of application of Gauss law there. And through this lecture, we have considered the basic things which are required to go through the electrodynamics, because this is electrodynamics is a very vast topic. It starts with the electric field produced by a static charge, and it is of course it is go to the time varying electric and magnetic field, time varying electromagnetic field it is, and finally we'll reach the Maxwell's electrodynamics. During the course, we'll have the Maxwell's equations, four equations. Again, we can apply this particular concept to non-conducting media also. Therefore, you are having there four vectors: electric field, magnetic field, then electric displacement vector, magnetic field displacement vector. We will have their polarization. We are having their magnetization in case of non-conducting media, and finally we'll discuss the actual effects produced by the sunlight, because the sunlight is the best example of electromagnetic waves. Further, we'll go for the reflection and transmission of sunlight through conducting media, non-conducting media, and we'll have the complete theoretical description of electromagnetic disturbance using this particular basic ideas about the electrostatic field, magnetostatic field, electromagnetic static electromagnetic field, and their time varying electromagnetic field, and finally the electromagnetic disturbance. Through this lecture, I got this opportunity to put my views about the electrodynamics before the TY B.Sc physics student of the complete Konkan region, starting from Thane district, Thane, Raigad, Ratnagiri, Sindhudurg district, and therefore I am very thankful to organizers for this particular opportunity to me. Thank you very much, sir. Thank you once again.